All right. So over the past few videos, we've talked about finding different ways to evaluate a limit where it exists, but we've already seen there are scenarios where it turns out that a limit does not exist. So for our purposes, you can categorize ways a limit fails to exist into three broad headings. We've already addressed the first one in the list. We'll talk about it again, and then mention what the others end up looking like. And I wanted to show you some pictures of what these things end up looking like if you were to consider stuff graphically. So first off, we've got this guy right here. We've talked before that if the left and right hand limits, the one-sided limits, if you will, of a function, do not match, then the overall limit does not exist. So I wrote it here as left and right hand behaviors disagreeing. Some people will shorthand this as just LHB not equal to RHB, or sometimes LHL not equal to RHL because left and right hand limits. But anyway, so let's take a look at an example of this in action that's not just like a graph I intentionally cobbled together to make it happen. So it's going to end up involving an absolute value function. So this is also a good primer on where to go find the absolute value command if you need it in your calculator. So it lives here in the math menu. So if you go over, use the arrow keys, move over, that very first entry there, ABS, that is your absolute value command. Like on an 84, I think it actually will put in the little absolute value bars. The 83, not so much. Anyway, so let's put in 5x plus 10 inside these absolute value bars, plus 10, and then we're going to divide that guy by, note the parentheses to close this up, x plus 2. And like I said, I'll close up my parentheses. All right, and I want to take a look at a graph of this guy. So let's see. Yeah, my graph window is still kind of, blown up. So let's do like not negative 50. I want negative 5 to 5. The scale of 1 is fine. And let's do negative 5 to 5 again. And I'll set that scale back to 1. And let's take a look at our picture. All right. Oh, okay. So yeah, this actually gets the point across pretty clearly. So the point I was interested in was x equals negative 2. If you've watched the previous videos, yeah, that's the place where like doing a direct substitution gives you a 0 denominator, but also a 0 numerator. In all of the examples we saw, when that happened, there was some way to kind of work our way out of it, and it turned out the limit existed. Here, the picture shows us, yeah, not so much. We kind of poke along here at what looks like negative 5, and then we do this like really big honking Mario jump up to the top all of a sudden right there. So technically the calculator is trying to connect dots that it shouldn't be. If we were to sketch this graph by hand, this stuff here doesn't exist. We just have this leading up, open circle right there, jagged jump, open circle right here, and then we just kind of keep on plotting along right there. So that limit does not exist at negative 2 because our left and right hand limits, as we've said before, imagining our little bug walking along here, he's getting close to what looks like 5. Over here, another bug would be getting close to negative 5. They're not coming to the same place. All right, so that's the left and right hand, limits disagreeing or right behaviors, whatever you want to call it. All right, so let's take a look at the next couple here. So we've got a function unbounded at the target point. So I'm going to clear out my absolute value function here. Let's just do relatively basic. So we'll do 1 over x, minus 1, and then we'll square it. So a little more involved. 1 over the quantity x minus 1 squared. Let's take a look at our graph and see what's happening in this case. So yeah, 1 over x, as you say, 1 over something squared is always going to be positive, so nothing lives down here. But you'll notice as we get close to the bad point, the 1, x equals 1 in this instance, coming over this way, our bug starts climbing and climbing and climbing and climbing, and he flies off eventually, like, you might say to infinity and beyond, like Buzz Lightyear. We'll get to more precisely what's going on a bit later on, in the course. Same thing's happening from this side. We're flying off that way. So yeah, that's what we mean by unbound. We can't like put a cap on this thing where it stops climbing. The graph always ends up exceeding any bound we set on it. You could also have unbounded behavior happen in the opposite direction. This graph, like if I go in and change this, I don't know, not much, but I'm just going to insert a negative right there. Like I said, doesn't change. Yeah, very minor change, but now we're always negative, and now, whoops, yeah. just like you might have expected, the graph has gone from up here to down below. It just kind of reflected across the axis. And now, instead of flying off into the great unknown, now it's like our graph is burrowing down into the center of the Earth. So, yeah, either one of those is an instance of what we call unbounded behavior. And again, we would say this function's limit at x equals 1 does not exist. So that's behavior number 2. The third, this is thing where I describe it as, oscillating wildly. I used to, write crazy oscillation when I would do this on, on board. For what it's worth, yes, that's how the word oscillates is spelled. That's often something students kind of trip over. My personal favorite is when they actually write osculates instead with a U here instead of an I, because, yeah. For those of you who don't know, yeah, that means kissing, and my functions don't kiss. That's just not what I do in the classroom. But anyway, so in terms of wild oscillations, I want to put together an example. And you may recall, like, our favorite oscillating functions are generally trigonometric functions of some sort. So let's take a look. The classic example is right here, sine of 1 over x. Now, before I sketch my graph, I'm actually going to zoom it back out because I kind of like the surprise factor this ends up, putting. One, make sure you're in radian mode. Remember, we've talked about that before. Mode, radian, learn it, live it, love it. Anyway, so we got that guy taken care of. But before we look at kind of a zoomed in graph, I'm actually going to go back just to the standard, 10 by, negative 10, to 10 window in each direction. The trig function, you can't really see an awful lot that's happening here. There was something that kind of, squiggled around right there, but, the rest of it's pretty flat. I mean, the sine function doesn't get any bigger than 1 or any smaller than negative 1 without you tossing like a factor in front of it. So that's what we've got right there. So let's try zooming in on this guy and see what happens. So I'm just going to use the zoom in command. You could manually adjust the window, but I think zoom in will do the job for us. So I'm going to zoom in on the origin. That's important. You might have noticed, plugging 0 into your function is bad news. But let's take a look at what's happening. Oh, yep. Now we've got this kind of like EKG pulse looking thing right here as it slashes around a bit. So that's it looks a little weird, but you might not call that wildly oscillating yet. It's kind of got like a couple of sharp points, but that's not what you might call wild. Let's try zooming in one more time and see what's up. Okay, yeah, that's... Now, my bounds are a little skewed at this stage because it's zoomed in past, the top and bottom values the sine function hits, but you can see we got a lot more like wiggling around in this instance. Let's manually go mess with these. So, xmin will do, negative, 0.1, and then I'll delete those other things. And I'll change that to a positive 0.1. And down here, let's set this back to negative 1 and positive 1. All right, didn't get rid of all you. There we go. Okay, so now our x bounds are very, very narrow at this point. So let's see what we end up getting. So yeah. Hopefully that feels a little wilder to you. That's not the nice, gentle trig function that you might have, traced out by hand, or my calculus instructor actually did just jump across the front of the room tracing out a sine curve with his hands. So, I probably would do the same thing given the opportunity. But for now, you can kind of see, and again, you can keep zeroing in on this thing and seeing it gets more and more nuts. I'll do one more. So, let's see. All right, so 0.01, negative 0.01 to 0.01. Yeah, this is not settling down at all. You can see the nutso spikes, and the more you zoom in, the crazier it gets. So yeah, that's wild oscillation. So those are the ways we're going to talk about a limit not existing. So you'll see this on the lab assignment. We just straight up ask you to produce graphs and just list the ways a limit fails to exist. So now you've got that. Congratulations. I do want to come back and investigate that absolute value function again, but I kind of need the board for it. So, it's also a good transition point to talk about the rather brief content of our next section.